Hi, human. So back to sequences of events. So remember in the last one we kind of decided that this is a good way to look at n events all at once and how they kind of sequence together. So we're gonna in this video we're gonna look at an example. Example 9.1. And let's see how this kind of might work. And we'll use our tree diagrams to help us. And basically what we're going to do is, let's see. So we want to flip a coin 2 times with the condition that if we flip a tails, then we draw a number between 1 and 3 out of a bag. Then once we've drawn a number out, we stop. So I flip a tails, I draw a number, and I'm done. If after the second flip, if I still get a head, so I get heads, then we consider that as a 0. Okay, so second is a heads, then we consider it as a 0. So let's first draw a tree diagram to kind of help us out, right? So I have, well, first I have 2 options, right? I can either pull a heads or a tails. And I'll put little indices to help because last time this made life a little easier. And here we have 1/2, 1/2. And this tails, we kind of already know what this is, right? This should give us either 1, 2, or 3. And we have 1/3 chance for each one because we're pulling a number out of a bag and it's either 1, 2, or 3. Okay. How about H1? So if I do heads, I'm allowed to do a second flip. So I can do H2 or tails 2. So again, here these are independent, and so the probabilities are going to be the same. They're not dependent on before. And then tails 2, we said, okay, whenever we get tails, we choose a number out of a bag, and here we have 1/3 chance for each one. What we also said is if I get 2 heads in a row, then we consider this 0. And this happens 100% of the time, so we'll give it a 1. Now, if we look at the tree diagram, remember this helps us because we just need to multiply things, right? So in this top area, we have 1/2 times 1/2 times 1, which is 1/4. This one here, maybe I'll use yellow. We'll do little lines here so we know where we're going. And then we'll do black. There we go. So here we have 1/2 times 1/2 times 1/3. This is 1/12. And you can see these are all going to be the same, right? The probabilities are the same. So I can just leave it 1/12. And this bottom one's here, this is 1/2 times 1/3. And that's it, right? I only have 2 events. So I stop here. So this is just 1/6. And you'll notice how these are the same for all of these. I guess I made these too close, but this should be 1/6. There we go. So, so let's add this. We'll do this. This is also 1/6. Anyway, so they're all 1/6, right? And so the tree diagram helps us because it allows us to really just multiply things, right? So remember what we're basically doing here, if we look at a given perspective, is this is the probability of heads 1, times the probability of heads 2, given H1 already happens. And then the third one is the probability that we get a 0, given that H1 and H2 and H2 happen, right? So it's the same thing here. We have probability of H1 times the probability of tails 2, given H1. And then finally, for this first one, we get the probability of 1, given that H1 and tails 2 happened. Right? So this is, we're starting to see where this trend of conditional probabilities is kind of really coming in. And so it also allows us to very easily kind of see, calculate probabilities, right? So if we ask what's the probability we flipped exactly 1 tails, well, if you look at it, flipping exactly 1 tails is this and this, right? Maybe I should do this in green. So it's this and this, right? So at this point, we basically have to just calculate the 2 parts. So what's the probability of this? This is the probability of tails of H so I guess of just tails 1 for the first one, plus the probability of h1 times the probability of h of tails 2 given h1, right? So this is equal to 1/2 plus 1/2 times 1/2, which is 1/4. So it's 1/2 plus 1/4 is equal to 3/4. So the probability of flipping exactly 1 tails is 3/4. Okay, so what is the probability? So next question is, what is the probability we pulled a 1 out of the bag? So in this case, I guess I'll do it in blue. This is looking at this case here and this case here. And so here we already have this first one written down, right? So what we have here is the probability of a 1 is given by the probability of h1 times probability of t2 times of h1 times probability of 1 given t2 and h1. But we also had a second way of doing this, right? So we can do probability of t1 times the probability of 1 given t1. And so here we saw what these are. This is just one, sorry, this one is not 1/6. This is, yeah. So this thing here, remember when we multiplied, this is equal to 1/12. Plus this part here is equal to 1/6. And we saw that from up here, right? So we get 1/6 here. And we get 1/12 here. And so 1/12 plus 1/6 is equal to 1/4. And the cool thing here is if you think about this, I could have chosen any number here. I could have said pull a 2 out of a bag, pull a 3 out of a bag, and I would still get 1/4. And if you notice all the way at the top, the probability of 0 is 1/4 as well. So in other words, what we did here, all of this is the same thing as putting 4 numbers into a bag and pulling out a random number. So these are two equivalent ways of doing the same thing, which is kind of bizarre. So if you only have 3 tokens and you want 1/4 probability, you can do this instead. You can flip a coin twice and then pull out of a bag. So there you go. If you ever need other weird ways to mess around with friends or something. So based off the previous things, what we have is that, like if you notice everything we've done, they're independent of one another, right? So flipping a coin and pulling a thing out of a bag, they're independent. So in reality, this equation here, for example, I can just write as the probability of getting a heads times the probability that the second one is a tails times the probability that I pull a 1 out of a bag. And so this idea really is the same independence idea that we had from before. So we just have a multiplication rule for independent events when we have more than 2 events. So if we have n events, we say they're independent if they are pairwise independent, as in if I take any 2, then I should be able to multiply them properly. So what this means, pairwise independent, means the probability of aj is equal to the probability of ai times the probability of aj, which is one of the definitions we saw previously. Now, what this can kind of expand into is we can actually just look at this as all the different things. So if I take the intersection, if I do and for everything, this is just going to be the multiplication of every single particular component. And that's it. So you can think of these as independent things. In the next video, we'll talk about a very famous problem in probability called the birthday problem. This one blew my mind when I first heard about it. So hopefully you'll enjoy it as well. So I will see you then.